Hello, everyone. Okay, let's get started. So, the plan is, last time I forgot to show you the Chebyshev inequality, which we are going to use. And then we are going to look at random projections and one important algorithm that is used to reduce dimensionality of your data, which is very important for dealing with data of high dimensionality. And then after that, we are going to do the singular value decomposition and principal component analysis. And after that, the clustering algorithms, the main one being based on singular value decomposition. So that's just in brief of what you can expect. So let me now just share my screen with you, and we can get started. Let me see. Okay. So you remember the Markov inequality that is kind of remarkably useful given how sloppy it is. Remember, this is just the inequality that says that the probability that a non-negative random variable will be bigger or equal than some number 2 is smaller or equal than expected number of x divided by t. So for this inequality to hold, all we need is that x is bigger or equal than 0, and that there exists the expected value of x, right? So it's extremely mild condition, and this, as we mentioned last time, this property is often not very useful because, for example, if t is smaller than the expected value of x, this would simply say that this probability is smaller than 1, which is smaller than something bigger than 1, right? If t is smaller than e of x, this side will be bigger than 1, and this is then completely vacuous because we know that in probability always has to be smaller than 1. However, it's remarkably useful inequality, and we are going to see now one of the most important applications of this inequality. And this is Chebyshev inequality, and Markov was a student of Chebyshev. So actually the teacher developed further the work of his student, it seems. So what does the Chebyshev inequality say? First of all, random variable x no longer has to be non-negative, but it should have both expectation and should have a finite variance, right? Then, rather than having probability of x bigger or equal than t, what we had in Markov, we actually have something much more useful, namely this side is, so the absolute value of x minus expected value of x. So this tells us how likely your random variable will be off its expected value, right? Probability, so you have your random variable, and this is its expected value x. So this tells you probability that you are significantly above or below the expected value of this random variable. And so you know that this will be bigger or equal than t with probability that is smaller or equal than variance of x. So remember, in Markov inequality, we had here the expected value of x divided by t. Now, instead of the expected value, we have the variance of x, and the bound is squared, which is very important because it grows much faster as t increases. So consequently, this bound becomes tighter and tighter. And notice, purely heuristically, this makes kind of perfect sense, because larger the variance, more likely it is that your random variable will go far from the expected value, right? Because the variance is the expected value of the difference between your variable and its expected value, right? So larger the variance, of course, more the values will be spread around the expected value, and larger the bound, of course. If you are asking for significant deviations from the expected value, the probability will rapidly decrease. Now, interestingly enough, as I said, so this is obviously a sharper inequality, but in fact, kind of somewhat surprisingly, it is proved just by using the Markov inequality. And the proof is extremely simple. So you see, first we notice that this, what's inside of the probability operator, is absolute value of x minus expected value of x is bigger or equal than t, but that's exactly the same. This holds just in case the square of this is bigger or equal than square of t, right? So this is exactly the same as this here. And now we just notice, right, that this expected value of this is just the variance, right? And this random variable, so let's call it y, which is x minus e of x squared, is clearly always non-negative. So the conditions for the Markov equality hold. And if we apply it, right, what do we get? Well, probability that the absolute value of x minus e of x is bigger or equal than t is, as we just noticed, is exactly equal to the probability that this random variable y squared is bigger or equal than t squared. So this is a probability. What we have here is probability that a positive random variable, namely x minus ex squared, is bigger than the bound t squared, right? By Markov inequality. So Markov inequality applies because y is positive, not negative. This will be smaller or equal than the expected value of y divided by the bound, which is in this case t squared. But the expected value of y, what is y? Y is just this, and the expected value of y is precisely the variance, right? So we can replace expected value of y with variance of x, and lo and behold, we get that the probability that x deviates from its expected value for more than t is bounded from above with variance of x divided by t squared. And this is another extremely useful inequality, right? So let's immediately get to a application of the Chebyshev inequality. So let's look at something called the law of large numbers. There are several laws of large numbers, and the literature is not completely consistent how they are about their nomenclature, right? So if we get a large number of independent sample of variable x with an expectation e of x, right? So in probability parlance, this would be independent, identically distributed random variables, but they are just the draws. You can think of this just as the draws of from the very same random variable x, right? So just several samples. So we would expect that the mean of these samples should be close to the expected value of x. And the law of large numbers actually bounds, sorry, something is happening here. And the law of large numbers bounds the probability that such a mean is further away from the expected value of x than a prescribed value epsilon. So assume that you want to get very precise measurement of my blood pressure, right? What you would do, you would repeat the measurement n times, right? Because you can never be 100% sure exactly at what point you could hear my heartbeat, right? So you repeat this measuring process several times, and you would expect, and if you have a good machine, expected value of the measurement should be the true value, right? So you would expect then if you average several measurements, right, that their deviation from the true value, right, it will be larger of epsilon with some small probability. And lo and behold, this probability is bounded by the variance of x, the number of measurements, and the tightness of the bound, so epsilon squared. So you see, this explains why when we want to make precise measurements, why we make several measurements and average them, because a larger number of measurements guarantees that the probability that you will err for more than epsilon will be smaller than the variance divided by n times epsilon squared. So if you double the number of measurements, your probability of error being, say, more than 0.1 millimeter of mercury will be less than half than if you just make n many measurements. So why is this a consequence of the Chebyshev inequality? Well, by Chebyshev inequality, we have the following. If we consider this average of random variables as a new random variable, you can call it y, then this random variable minus the expected value of this random variable will be larger than epsilon with probability that is bounded from above by the variance of the random variable y, namely variance of the mean of random variables from x1 to xn, divided by epsilon squared. Now, here, it's easy to see that the expectation of the mean is exactly the expectation of the of every instance of this random variable x, right? Because expectation is linear operator, n can go outside, and e can get distributed through the sum. All of these have the same expected value, so you get n times e of x divided by n. This is e of x. So we know that we can replace this just by e of x. Okay, let me see. We have some questions. Sorry, I should have looked earlier. In the proof, we are comparing to t squared, but in Chebyshev, we are comparing t. Why are they different? Well, that's the trick. So why do we have, let's just very quickly look. Let me answer your question. You see, because the bottom line is that this is, we don't like absolute value because it's non-differentiable function and difficult to deal with. So we simply noticed that this is bigger than t if and only if its square is bigger than t squared. And then the expected value of the square of this is precisely the definition of the variance. And of course, when we square the left side, we have to square the right-hand side. So the variance is in fact kind of a quadratic object, right? So it makes sense that it's divisible, divided by t squared. Okay, so the second question is, why did we assume that the expected value e of xi is equal to ex? Because this is in the law of large numbers, okay? In the law of large numbers appears to repeated experiments. This is formalized usually by saying that random variables x1, x2, xn are independent and equally distributed. So for that reason, they all have the same expectation. But how to think about that? They are not different variables, random variables. They're just, you can think of this as draws from the same probability distribution. So they are the values, repeated measurements. This is what is the essence of this. Why do we take the mean? So you want to measure something very precisely way before statistics, kind of advent of statistics. We knew that if we take, if you take several measurements and you average them, that you get more accurate result. Intuition being that you are equally likely to err above and below the true value. So when you find sum of several measurements, the errors are likely to cancel out rather than to accumulate, right? Because they are likely to be equally positive and equally negative, right? So I hope this answers well, yes, so if you have a different sensor, then E can be different, but it's not, you know, it is not the same. You see, expected value will be equal, right? The expected value will be equal even if the sensors are not of the same quality. What is going to be different is their variance. Kind of lousy sensors will have large variance, but expected value is related to being unbiased. So if your sensor is not such that it always overestimates or always underestimates the measurement, then then the expected value is the true value. So then this then boils down to the probability that the mean of your measurements minus the true value is in error bigger than epsilon, right? So now what we saw is that expected value of the mean is just expected value of x, right? So we will, that's about the expected value. Here we have the mess of variances. It's easy to see, you can do it as an exercise. Variance is not linear, then n, when n goes outside of variance, it has to be squared, right? Because variance is quadratic. It's expected value of x minus expected value of x squared. So taking out n will cause the squaring of 1 over n. And now notice what's important is that this equality holds regardless or not the random variables x1 to xn are independent or not. So even if they are independent or if they are correlated, then expectation still is linear. However, for the variance, and this is why we are assuming that the errors are independent from first to the second to the third measurement and so forth, right? Then the variance of independent random variables is sum of the variances. So we will then have, right, we are now working on this. So this we have replaced by the expected value of x. And here, if you take n outside of the variance, it becomes squared. And then variance of the sum of independent random variables is equal to the sum of the variances. So in this case, by our assumption, all variants are the same. So if the sensors are not the same, this calculus won't exactly go as here, but of course, instead of just having single variance, you will be getting here 1 over n times sum of the variances, but the estimation still holds true. It's just that it most used when the random variables are equally distributed. But as you mentioned here, yes, so what we are showing here is just for the case of independent and equally distributed. So equal distribution doesn't doesn't matter that much. Most of the calculus will go if they are not equally distributed, but of course then this won't be just expected value of 1 over n times expected value of a single occurrence x, right? But you can carry on with calculation. What is truly crucial is that they have to be independent so that you can distribute variance inside. Otherwise, you're stuck with expression as is, and it's not as useful as when you can distribute the variance inside. So that will be n times variance of x divided by n squared, and lo and behold, you get variance of x divided by n times epsilon squared. So to summarize, regardless of whether x are independent or not, for as long as they are all unbiased, namely the expected value of each of the variable is equal to the true value that they are supposed to measure, right, in this main example. So then the expected value of the mean will be precisely the expected value of each of the variables. The variance will be variance divided by n, right? Because here you will have n squared going outside and then distributing, if they are independent, distributing v inside, it will produce n times v divided by n squared, you get this. And finally, probability of deviating from the true value is bounded by V divided by N and epsilon squared. So this explains why consecutive measurement, why repeated measurements of the same quantity and averaging improves the estimation. Averaging will not change the expected value. It will reduce the variance. So this estimator has the variance that is 1 over n of a single measurement, right? So if you repeat it 10 times, the variance of your estimator will be only 1/10 of the variance of your measuring device. But even more importantly, probability. So this is just kind of cumulative measurement. Here is expected value, and here is another expected value, namely variance. But this here gives you probability that you will be off the true value by more than epsilon, that it is smaller than variance divided by n times epsilon squared. So this shows why, in fact, taking multiple measurements and averaging, what people knew from antiquity, improves the accuracy of the measurements. Very good. So this is Chebyshev inequality and its application on the law of large numbers. So now let us move to our next topic, which is random projections and the famous Johnson-Lindenstrauss lemma, which is really, really useful for people who do databases, as we will see later. And there is a much more detailed exposition in the textbook that I gave you a reference to. Okay, so now, first kind of thing that we have to do is I have to teach you how to stop trusting your own intuition. So a good analogy of what we are going to experience now is when they train fighter pilots, right? The thing is that if you are making lots of sudden maneuvers and going upside down and funneling left to right and whatnot, your inner ear gets totally confused. And you can bet your life that you are flying in upward position where you are actually your head down, simply because the inner ear sensory mechanism got totally confused. So the way to fly a plane when you do this sudden maneuver is to trust only the instruments. So in the plane, you have this horizon that tells you exactly how tilted you are. And the hardest thing for young pilots to do is to overrule their feeling, say that they are flying upside down, even though they are actually flying horizontal, flat, with heads up. And it takes a lot of practice to teach your body to do maneuvers according to what you see as instruments telling you rather than what you feel. Okay, so how is this related to what we are going to do? Well, our only intuition about the geometry is based on R3, on three-dimensional Euclidean space, even though, of course, Einstein tells us that the space is not Euclidean, but it's curved. but locally it looks pretty much like Euclidean space, unless you are very close to a black hole, right? And you can also imagine geometry in R2, because you can draw things on in a plane. But once the dimension goes up, you have to stop trusting your intuition and start trusting the formulas. Even though formulas might tell you something that looks totally crazy. So this is what I'm going to show you now, a few interesting, crazy things about high dimensional space. So let us now make the following thought experiment. So we consider a Gaussian random variable x with zero mean and variance that we choose only out of convenience. It's really not at all important, just formulas are neater. If you set variance, you can set it to 1 and then formulas get a little bit messier, but not by much. But let's set the variance to 1 over 2 pi. So what does the Gaussian with variance 1 over 2 pi look like? Well, this is the formula, the density of a Gaussian. If I put here 1 over 2 pi, this disappears because 2 pi times 1 over 2 pi is 1. That's the only reason for our choice. And then here we have 2 divided by 2 pi. 2 and 2 cancel out and pi jumps above, and you get e to the minus pi x squared. So this is what we are going to do. We are going to define a vector, right, in a very large high dimensional space by calling our random number generator, and of course all programming languages and all software packages like MATLAB have random number generators that run with the density function that is the normal density or Gaussian, right? That's normal means Gaussian. And we are going to define coordinates of this vector, right, by running for each coordinate separately, independently, running the random number generator, okay? And see what we get. Now, by the way, I should tell you, why are we interested in extremely high dimensional space? Well, it's totally non-mathematical reason. The reason is totally practical. For example, assume that you have a huge collection of articles, right, in your database. For example, this IEEE Explorer, right? And then you get a new article and you want to see if you have in your database similar articles. You want to find what are the articles in your database that are the most similar to the new article that you just got. Well, there are many ways to measure similarity, but one of the simplest and most popular one is just by relative frequency of keywords, right? So each document, okay, you can extract the keywords or just all important words except the propositions, articles, and similar. And then you can count how many times each word appears and divide each number of appearances by the total number of words, right? This will give you relative frequency of each word in that document. And the belief is that if two papers are related, they are on the same subject, then they are very likely that they will have the same keywords, the same important words, and that each keyword appears with approximately similar frequency. Why? Well, if you are writing an article about chimps, then very likely word chimp or its plural will appear quite frequently. And if another article is is about say global warming, then word chimp probably will, if at all, will appear far less frequently. So the topic words, the idea is then the topic words, the same words will have the highest frequencies. So the idea is you should be looking in your database what are the papers that are as close as possible to your new paper in terms seen as vectors. Now vectors here will have one coordinate. Yeah, that's not good to draw it that way. Let me, the coordinates that you will have will be keywords. So you can see them as arrays, right? And these are all the words from your dictionary of important words, so keywords in alphabetical order, right? And then here is how many occurrences of each word you have. So this vector, what is its dimensionality? Well, its dimensionality is how many keywords you have in your dictionary. And English language has, according to, I was just looking at that, it has about 1 million words, but to be well educated, you have to know about 100,000 words, the meaning, right? So the dimension of this space is 100,000, right? So what we are addressing in all this that follows is looking for nearest neighbor to a vector in a space of dimension 100,000 is a computationally infeasible number if you have lots of vectors and you have to do complex operations, for example, finding their cosine symmetry or whatever. This is going to be an extremely hard problem. So what we want to do is we want to somehow collapse this high dimensional space into a space of smaller dimensionality, maybe a few thousand only rather than 100,000, but that preserves the features from your original space. So it's a very practical problem, how to deal with data that live in a just unmanageably high dimensional space. Another example for those of you that study biology is looking at, I think it's called microarrays, or this can be seen, for example, a song, and the song consists of sampled values, right? And a very crude way of determining whether two songs are similar is by looking at some form of distance between these two strings of values. But this can be in tens of millions, or actually even more than that, hundreds of millions of samples, right? So dealing anything with signals is or for example, they can be measurements of, say you have a bunch of temperature measurements and you collect the measurements over a long period of time, and you want to figure out whether two places on Earth have similar changes in temperature, right? Well, you would have to compare two signals that live as vectors in vector space of very high dimensionality. So this whole business is geared towards dealing this one of the main problems of data science, which is handling vectors that live in a vector space of exceedingly high dimensionality, which translates into trouble because everything gets complicated when the number of dimensions is very large. Okay, so, and the idea how to handle this problem is precisely the idea that we had in our universal hashing. Except that here we won't be projecting on a single vector. We will draw a bunch of random vectors and project the whole space, maybe a few thousand vectors, and then project the whole space on the subspace spanned by only a few thousand vectors, right? So the dimensionality of the whole space will be hundreds of thousands or maybe even millions, but we will reduce it to a space of dimensionality, quote unquote, only a few thousands. But the idea is the same: draw random vectors and project onto them. And now it sounds totally counterintuitive. Why would projecting on random vectors be better than projecting through on some carefully constructed vectors? Well, this is where the randomized algorithms come into the play, and you will see in a moment why this is a very good idea. So with this motivation that we want to draw random vectors, we will do that using a Gaussian distribution, and we decided on variance 1 over 2 pi. So now, notice, because the expected value of a Gaussian is 0, right? Because a Gaussian is equally likely to be, the density is symmetric around the origin, so the density about equal distance, well, this is not exactly equal distance on my picture, but, oh gosh, no, it doesn't want to erase it. Oh, well, use your imagination. So this is supposed to be x, oops. And this is also supposed to be x. You are equally likely, the densities are symmetric around the origin, so you are equally likely with equal probability to hit -1 as to hit 1. Of course, not probability, but density probability for continuous case. So the expected value of Gaussian is 0. So the expected value of x squared is the same as expected value of x minus e of x and then squared. Why? Well, simply because this is just 0. So e of x squared is just the expected value of this difference squared, but this is precisely the variance of x, which is 1 over 2 pi, right? So now, how do you find the length of your randomly generated vector? Well, you have to sum the squares of its coordinates. So lo and behold, this is what we do here, but we also divide by d, right? Because well, you will see why we do that, because the expected value of this is, I can go with expectations inside. So this will be expectation of x1 squared up to xd squared, but they are all equal to whatever is the expectation of this Gaussian. And then d on the bottom and d on top will cancel, and you get just the variance, right? So what does this mean? Well, the length of a vector, right, or its norm, how it is usually called, is square root of sum of the squares of its coordinates, right? And now we see that the expected value of sum of the squares of its coordinates divided by d is constant, is equal to 1 over 2 pi. What does this mean? This means, so the expected value of length of x squared is d over 2 pi, which means that on average, the length of your vector x is equal to square root of d divided by square root of 2 pi. So if you totally randomly generate your vector, all these vectors will be approximately of the same size, the same length, and their length will be square root of the dimensionality, right? So if you, and you see, because of the law of large numbers, if d is large, right, then by the law, this is why we divided it by d, now you can see, by the law of large numbers, this guy, this mean, will be very close to the expected value, namely the variance. So if I generate 10 of such vectors, all 10 of them is approximately of the same length, right? So this is basically dimensionality reduction. Yusuf says, yes, this whole story, the whole business is just dealing with what's called the curse of dimensionality. All our methods, deterministic methods, for example, computing integrals or just name it, they all collapse in high dimensional space. The deterministic ones, right? You cannot split the domain in small intervals because the number of boxes that you will get will be truly gigantic, right? If you split 10 in your interval into 10 boxes, into 10 sub-intervals, and you have 100,000 dimension, the number of boxes will be 10 to 100,000. What can you do with that? Nothing. You cannot compute, right? So the only ways that we know of to deal with such problem is by using randomization, by literally integrating things, by sampling the space and just counting how. So assume that I give you the following problem. You have a curve, right? And we know that this is, say, of length 10, and say the we take this is, say, of length 1, right? And I ask you to find the integral of the function, and I drew this for you, and the only thing that I give you is a dart. How would you find this integral if I give you this curve drawn on a rectangular piece of paper, if I just give you a dart? what would you do? How would you compute integral using a dart? Throw enough darts at the rectangle. Exactly right. You count only darts that end up in the rectangle somewhere, and you count what portion of them compared to the whole portion, the total number of darts. The ratio of these will be precisely the ratio of the integral with the total surface area of the rectangle, right? So this is why random processes are, this is essentially how what you have to do in high dimensional space. You have to quote unquote throw mathematical darts, namely randomly generate points, and then simply count how many of them are underneath the surface that is the boundary of the region over which you want to integrate. Okay, so so at the moment, what we just discovered is if you have a vector space of dimensionality 100,000, say, and you generate using a Gaussian a random vector by randomly generating its coordinates using the Gaussian, right? We discovered that all these 10 vectors will be approximately of the same length, and that length will be precisely the square root of the dimensionality divided by square root over 2 pi if your variance is 1 over 2 pi. So the length of your vector will of course depend on the variance. Larger the variance, longer the vectors will be, but on average, all 10 vectors will be very close to square root of d in size. So try for yourself in your favorite language, generate say 10 vectors in the vector space of dimensionality 100,000. So simply generate 10 arrays of values, each value randomly drawn from a fixed distribution. Even doesn't have to be necessarily Gaussian, but Gaussian is the easiest to deal with. So simply draw all coordinates and find the length of this vector. Simply find this expression. What is the square root of the sum of the squares of the coordinates, and you will see that all 10 vectors will be of approximate size, some fraction of square root of d, right? So if you find the ratios of their sizes, they will all be very close to 1. Okay, so by the laws of large numbers, what you can see is, right, by the laws of large numbers, we know that the expected value of this is just the variance of your random number generator. And you have this inequality, right? The probability of this event that you deviate from the variance more than epsilon is smaller than this. But we know that this on top is length of x squared, we divided by d, variance is 1 over 2 pi, and this will be, why is this so small? This will be so this sum of the squares divided by d minus 1 over 2 pi will be bigger than epsilon, then variance of x squared divided by d times a squared. So you see, as d, so this is fixed. This is just which random number generator you use. And say epsilon is something small, say 0.1 or whatever. right? And you can see as the dimensionality increases, this converges to 0. So say if epsilon is 0.1, then this is 0.01. And if this is, say, 100,000 times 0.01, this is 1,000. So it will be variance of x squared divided by 1,000, which is very small. So the probability that the square of the length of your vector is larger than d over 2 pi will be very small, which means that the deviation from 1 over 2 pi will be very unlikely. So this shows that if you randomly generate vectors, all of them will be approximately of the same size. But things become even more than that, more than that. What is also true? Now assume that you generate 2 vectors like that, okay, independently, right? And you find their scalar product, right? If you find their scalar product, this will be expected value of the scalar product will be just product of pairwise coordinates, but they are all equally distributed. So this is d times expected value of xy. But if you generate the 2 vectors independently, then the expected value of xy is equal to expected value of x times expected value of y. And we choose our probability distribution to have expected value of 0. So this will be approximately 0. You see, intuitively, if x's and y's are independently drawn from the same probability distribution, then probability that they are of equal sign is equal to the probability that they are of opposite sign. So on average, this should just cancel out. So what does this mean? It means something terribly important. If you draw 2 random vectors independently, in all likelihood, exactly what Yusuf says, probability that they are orthogonal is the highest. Yes. So in all likelihood, they will be either almost orthogonal or orthogonal. What does it mean, almost orthogonal? It means that this sum, their scalar product is small. So in all likelihood, they will be at an angle of 90 degrees, amazingly enough, even though they are randomly generated. And now this gives you a hint why we generate random vectors. If you generate, say, 10 vectors, we will show that in all likelihood, every 2 of them, they are pairwise orthogonal, right? And this means that they will be, and they're of the same length, square root of d, right? If you divide their length by square root of d, you get an almost orthonormal coordinate system. And this is why it is so useful to project on randomly drawn vectors. Okay? Good. But we can make this more rigorous, but this is a good place to make a short break so that my throat recovers. Okay. Maybe I should pause the, if I only knew how to do that. How do I pause Zoom? Let me see. Oops. It was not very clever. Oh, well, we will start. Okay, let's continue. Okay, so this theorem, it's just technical mumbo jumbo, so we will not prove it, but you can find it in this free textbook that I recommended on the course webpage. Okay, this is Blum, Hopcroft, I believe, and Cannon. And what does this lemma says? This lemma simply formalizes what we just saw, making it a tiny bit more precise. Namely, it gives an explicit bound for probability. So assume, so the setup is just what we saw. We are drawing in d-dimensional space a vector, okay, a random vector. What we saw is that, and this time we take unit variance in each direction. Okay, so this is the probability distribution because, right, it's independent draws, so it's just the product of Gaussian probability densities. So what did I tell you? I told you that if you draw such a vector, its length will be, with high probability, just square root of the dimensionality. And this just makes it exact, namely, the length of your vector will be square root, will be off this square root of dimensionality, right? So we know that this is approximately equal to square root of d. How close it is? Well, this difference will be smaller than some constant beta with a probability that is at least, let me increase this, that is at least 1 minus 3e to the minus beta squared divided by 96. If you are curious why 96, you would really have to suffer through the proof and see how this comes, from which constants it comes. So what does this say? It essentially says that probability, say d is 100,000. No, let's take it 10,000 so that it has a nice square root. So we are now, so d is 10,000. So square root d is equal to 100, right? So this will be square root of d is 100, and say for beta we take for beta let's take how much shall we take? Say 5. So what does this say? It says the following, that the probability that the length of x minus square root of d, which is 100, will be, say, let's switch the direction, is bigger than 5, with probability smaller than 3 times e to the minus 5 squared divided by 96, which is smaller than 3 times e to the power minus 25 divided by 100, which is 1/4, right? 3 times e to the minus 1/4. Well, let's take d to be even larger dimensionality. So the bottom line is this. This quickly becomes a very small number as beta increases, and of course, when d increases, the significance of beta will decrease, right? So let's do it to make sure what we are talking about. Say the dimension d is, say, equals to 10 to the 6th. So square root of d is equal 10 cube. Okay. So then this says, and say d, we keep it to be so say we set beta to be equal to 10. Well, let's take beta, so this is 1000, beta can be 100, right? So now we have the following estimate, that the length of our vector x minus square root of d, right? Probability of this being bigger than 100, right? So what is this? This is probability that the length of x minus 1000 is bigger than 100. So you deviate for more than 10% of the square root of d, right? Will be smaller than 3 times e to the minus, now beta squared is 10,000. It's what is beta squared? Yeah, it's 10,000 divided by 100, which is equal to 3 times e to the minus 100. E to the minus 100 is extraordinarily small, right? Because e to the x looks like e to the 1 over, so this would be, okay, so this is 3 divided by e to 100. So e to 100 is gigantic. So this will be an extremely small number. So if you are in a vector space that is of dimensionality 1,000,000, then the length of a randomly chosen vector will be 1,000 plus or minus 100, 10%, with a ridiculously small probability of 3 divided by e to 100. So this is called the Gaussian annulus theorem, how to think about that. It simply tells you the following. If you are doing the coordinates by randomly choosing using a Gaussian, with all likelihood, all the points that you randomly generated will be in a thin shell around the ball whose radius is square root of d, right? Because the probability to differ, say, more than 10%, we saw is minuscule. So if you randomly choose our vectors, they will be almost of the same length with a huge probability. Beta cannot be 0, that's correct. Beta cannot be 0. So this means that in a high dimensional space, if you generate coordinates of your vector randomly, all these vectors, their tips will all be in a shell around of radius square root of d, right? That's exactly with extremely large probability. So all the vectors that we generate will end up with very high probability within shallow, just very thin shell of radius square root of d. And as I said, the proof of this is not terribly complicated, but a lot of algebraic mambo jumbo that doesn't have really, you can read it in the book and see how it works. But intuition is completely clear. Randomly generate vectors, well, their tips will all be in a thin shell that is on the distance square root of d, where d is the dimensionality. Okay. Now, next thing that we want to do is this. This, we come to the place that is really kind of totally counterintuitive. So don't even try to imagine it will go totally against your heuristics. What it says, what we are going to do now is the following thing. Rather than looking through the formulas, I want to first describe to you what it says. So first thing that we just saw is that most of the mass, so to speak, most of the measure, mathematically speaking, in a high dimensional ball is in the kind of shell, thin shell of a radius up to the center here, square root d. So most of the mass is here. Even though this is a thin shell, what's inside here is of negligibly small mass as the dimension increases. This sounds totally counterintuitive because in low dimensional space, obviously, there is more mass inside the circle than in a thin strip around it. The one way of seeing is that in a sense, the length of this steel strip is gigantic, right? So that's why, but important thing to know, and this is what these theorems show, is that most of the mass in high dimensional ball resides near the surface. How do we know that? Well, we just showed that if you randomly generate your vectors, with high probability that it will be within this annulus, right? If the mass was inside, then when you randomly generate vectors inside, you would get lots of points inside. But we showed that the probability to get points inside is very small, which means that the measure, the volume, so to speak, of the sphere is mostly near the surface. Right? This is kind of crazy, it's all right, but wait until you see the second statement. The other thing about the sphere that this theorem proves is the following. You take your sphere, this is more of a potato than sphere, but, and then you do the following. So this is the cross section. Then you take parallel with this plane, another plane on top, and parallel with this plane, another on the bottom. And then you look at the part of the sphere that is between these two planes. Okay. So you cut your hypersphere by two parallel subspaces, so to speak. Well, it's not subspaces, affine spaces, right? Because they are translated of the one dimension less. And what you get is that most of the mass is in this slice near the equator. How does this sound? It sounds totally absurd, right? You cut the hypersphere with two and d-1 dimensional planes, so to speak, whatever would correspond, that are parallel, right? And the equator is in center. The mass that is in this, how would you call it, these domes is negligible. Most of the mass is, so now how paradoxical is this? First we heard that most of the mass is in a thin shell around near the surface of the ball. And now I'm telling you, it's not only that it is all in this thin shell, but if you cut with two parallel d-1 dimensional planes that are very close to the equator, right? Most of the volume will be between these two planes, namely close to the equator. And if you ask me if I can imagine that, I tell you, you guys are nuts. No one can imagine that, but this is where mathematics comes into the play. And now all what we are doing here is to handle high dimensionality in databases, not because we are idle mathematicians, right? All what we are interested in is how to avoid the curse of dimensionality, okay? Now, despite, so we will ignore what our intuition tells us, namely that this is completely balloony, that this doesn't make any sense. We are going to do the calculations that will show that this is true, and then we are going to construct an algorithm according to that. Now, why is this fact important? First of all, this algorithm, the first one, is important for the following reason. Excuse me. For the reason that says, if I generate a vector using Gaussians to produce its random coordinates, its length will be square root d if my variance was 1. So no matter how, for as long as the coordinates are random, the length of each vector, if I define several of them, will be approximately square root d. Okay. Well, now Yusuf is asking an interesting question. So it's between the planes on the shell. You know what? No. And the reason is these planes are not planes, they are d-1 dimensional spaces. Okay, so obviously it's impossible. I mean, I can do the same with two planes like this here. And now my argument will tell me that most of the volume is also here. Well, the only conclusion is that these two guys intersect over set with large mass. And lo and behold, that's exactly true. But saying that, you know, it's impossible, yeah, it's not quite right to say that it is both in this strip, because if I take orthogonal strip, what happens then? But in many dimensions, that's exactly what happens. Why are we interested in this? Well, look at a very important consequence. So let's see, I'm telling you that if I cut my sphere like this, then with all likelihood my vector, so say I generate one vector and I can rotate my sphere so that it's pointing towards the north, okay? And now I generate another vector. Where is this vector going to end up? Its tip, where it should be, if you know that the vector, that all the mass is between these two hyperplanes. Where will this, can it end up here? Well, no, if the very small amount of volume is in the this cap, right, in this dome, in this slice of the sphere, if this has very low mass, if I randomly choose the vector, it won't end up here. Where should this end up? Between the planes, exactly. Yusuf says it has to end up here. But if it ends up here, right? So it's between two planes. What can you tell me if I project this vector onto the first? So let me say that's a vector. Let me change the color. This is the center, and my vector is, say, this. And then I project it to the first vector. The fact that it is in this narrow strip, what can you tell me about the size of the projection? It will be of very small length, exactly. Anthony is right. So this means that if I have two vectors, right, randomly generated, the second vector is in all likelihood almost orthogonal to the first vector, right? So this is why we need this mambo jumbo. Namely, you generate one vector, you rotate it just for the purpose of visualization towards the north. You know that most of the volume is in this thin slice. So if I randomly generate a vector, in all likelihood, it will end up in this thin slice because most of the mass is there. But if it's in the thin slice, right, then its projection to the first vector will be very small. And you can see the value of this projection is the scalar product of these two vectors divided by the length of the second vector, right? So anyhow, the bottom point is, why is it so? Scalar product is x1, y1 plus xn, yn. And xr and y's are equally likely to be positive and negative. And they are also equally likely to be of the same size, of the same sign as of the opposite sign. So if you sum up these guys to find their scalar product, this is bound to be small because most of the stuff will cancel out. So this is another way to see why any two vectors are approximately orthogonal, because right, their scalar product is in all likelihood close to be zero if dimensionality is high, because there will be heaps of cancellations here. Okay, so now, you know what? In these slides, I went through the pain of calculating exactly the probabilities. But the content, so what are these calculations for? These calculations are not for any rigor, but what I told you sounds completely bizarre, right? So how do we, what do we do when something looks bizarre? Well, then we have to calculate. If I were a physicist, someone told me, look, this light, that's a stream of photons. Oh, and by the way, it's also an electromagnetic wave. Well, is it a wave or particles? Is it like little balls coming and hitting me? Or is it like sound waves or electromagnetic waves? Well, it's both. Well, how can it be both? Well, no one understands how it can be both, but math works out. And when you compare it with measurements, lo and behold, they perfectly fit. So then we abandon our hope to truly understand how light can be both particle and wave, and we just live happily with math that describes them. In the same way, you see, I told you something totally bizarre. I told you all the mass of my ball is around the surface. Oh, and by the way, it's also between two planes that are close to each other. This sounds completely crazy. It's just sounds plain stupid. So for that reason, I went through the pain to compute the probabilities, which you can read on the slides, right? And verify that, lo and behold, what I told you, mathematics proves. This doesn't help a bit of me understanding why this is true, but that's my problem. Who cares? You see, the trick is, if you implement this, it's a piece of cake. I mean, what are the vectors? You call a random number generator to fill an array of, say, 100,000 objects, right? Then you call your random number generator also to fill another array of the same, and compute their scalar product and see what you get and how it compares with the length of these vectors. So you can even do empirical tests, just like physicists can do tests that verify that light are particles and light is electromagnetic radiation. Yeah, well, you can simply program your computer and verify all these probabilities numerically. And lo and behold, you will get that these bounds are actually pretty pessimistic and things are even more extreme when you program this. So do yourself a favor, just fill a bunch of arrays with randomly generated, normally distributed values and see what are the values of the scalar product. And you will, of course, discover that they are almost zero. right? Especially compared to the modulus of the vector that will be large. If you do it with array of size 10,000, this vector will be of length 100, right? Square root d. So this is not, so I put here the proofs of these things, and they are only so that you can read through them and lo and behold conclude that what I tell you, as stupid as it sounds and as bizarre as it sounds, that it's lo and behold it's true, right? And then on top of it, you can also do experiments with your computer and show that indeed these things hold. So, so don't be kind of deterred by this math. As I say, the only purpose is, if you are mathematically inclined, read through the proofs to see that I'm not telling you something false, right? And how another way to see, so I'm telling you that most of the mass of a sphere is near the equator. Look, a very simple proof why this is so. Well, consider another ball whose that is, say, 99% of the original radius. Okay. And assume that this is a ball. We start with a ball of unit volume. Okay. Then, okay, so if you have a ball of volume V and radius R, how are volume and radius related in d-dimensional space? In 2 dimensions, the volume is surface area, right? And if this is R and R, it's related as R squared. If it's if you have, so if you take a ball of radius 1 and you take a ball of radius R, so this is V1, this is VR. How are V1 and VR related? What is the V1 divided by VR? It's like 1 divided by what? R to the D. Very good. Who says that? Yusuf. Okay, Yusuf, you get extra points for class participation. Send me an email. So this will be as 1 over R to the D, right? Well, if I reduce the radius from 1 to 0.99 and I take it to a large power D, say I take 0.99 to the power 10 to the 10, right? How big is this guy going to be? It's going to be almost 0, because if, so even though I tiny little bit reduce the radius, its mass is going to disappear, because when I take it to the power, whatever D is, it's going to be extremely small. So the volume of this sphere of 0.99, say, radius, and this sphere of radius 1, the ratio between the volumes of the big ball and small ball, right? The small ball will have volume almost 0, because 0.99 to a large power is extremely small. So nothing is here, most of it is near the surface area. And the same applies for this crazy idea with two parallel planes, right? If I take a vector and then randomly choose another vector, it will be almost perpendicular. But in order to be almost perpendicular, this precisely means that its projection to this guy is small, which means that it has to live between these two hyperplanes. So nothing unusual is happening here. All of this, as crazy as it sounds, when you see how volumes and scalar product, how they scale with increased dimension, it becomes kind of natural, as weird as it is. Okay.
Alex,
Yes.
do we know like the distance between the two planes?
Sorry, just a second, let me put my volume up. I can barely hear you. Can you say it again?
Do you know what the distance between the two planes are?
Okay, that's a very good point. So we will actually, that's our next task.
Oh, okay.
We are going to give exact probability depending on the distance. So clearly, if you make a distance a little bit larger, right, the probability that it's in between will increase even more. If you reduce it, it will decrease, but not very much. Unless you have to really slam them together to get very low mass. So that's an excellent question. And this is our next topic. So all of this is actually, maybe let me just see. Yes, okay. So here is what you are asking. So this inequality says, so it says the following. If you have your hypersphere and you have your equator and you have your cutting plane, okay, and the distance between this is, let me see so that I don't make a mistake. It is, if I remember it correctly, is c over square root of d minus square root of this. Let me just see. Let me just see. Here it is. C over square root d minus 1. Okay. So this distance here is c divided by square root d minus 1. So clearly c can be bigger than 0 and smaller than square root of d minus 1. So if you have the 10,001, if your d is this, then c ranges between 0 and 100, right? So this is, say, c divided by 100 if for d like this. Now, then the ratio of the volume that is in between, okay, so the ratio of the whole hemisphere So this is H. And A, which is just the volume of the cup. So A is volume of the, how would you call it in English? That's a dome or cap. Is it cap a good word? Spherical hemisphere, very good. But it is not really hemisphere because it's a little bit cut, not exactly near the equator. So it's, if you take a ball and that dome, okay, a volume of the dome, and H is the volume of the whole hemisphere. Right? So in 2D, in 3D, this looks almost the same. So A is this volume, and H is, let me do it in green. Oh, H is this thing whole, right? So A is just above this parallel plane, and H is if you go straight through the center, right? So in 3D, this looks like, well, that's almost the same. But what we show here is that this ratio of A over H is smaller than 2 over C times e to the minus c squared divided by 2. Okay, so if let's take for C, let's take, so this here is square root of D, okay? And let's take, which is in our case, because we took D to be 10,001, so this is 100. So say C is something small, say C is, if the radius is 100, say C is equal to 10. Then A over H will be smaller than 2 over 10 times e to the minus 100 divided by 2, which is e to the minus 50. E to the minus 50 is nothing, right? It's just amazingly small, right? Because, right, c is squared. So the volume of this dome compared to the proper hemisphere is negligible, right? And we know, and this is very conservative estimate because computations are difficult, so we make kind of very rough estimates just to make the numbers work out without the formulas becoming unwinding. So you see, if you take this to be C to be, so in a cross section, right, you will have something like this, right? This is C over square root of D minus 1, which is C is 10 divided by 100. So this is 1/10. And if it's 1/10, the mass that is outside of these two parallel slices is smaller than this, which is just a ridiculously small number. Okay, so look, okay, so let me see what is next that we want to do. Yeah, next, okay, so we are getting there. Next, I want to show you what kind of estimates you can get when you have several such vectors, because more vectors you draw, more likely things are to go wrong, right? Maybe even if likelihood that some vector will end up outside of this slice, of course, increases with the number of vectors. So we need estimates relating this probability to a number of vectors, and then we will show purely intuitively without much worries about this integration and all that stuff, how we use this for dimensionality reduction for Johnson-Lindenstrasse. So please read this at home, and we are going to continue on Wednesday. How's that? Good. Okay. So I'll see you on Wednesday, and then yeah, we will see how we progress.
Alex,
Yes.
the previous calculation of the ratio between A and H, do you mean that it's the number of points in A versus the number of points in H? Or is it the volume of A versus the volume of H?
Volume. Okay, so there is no, so it's the volume. Okay, so that's very good question. It's a volume, but this volume, okay, so assume that you have a rectangle or a square with another inscribed square that is half the surface area, okay? And you start randomly throwing darts at the larger square. How many of them are going to end up inside the smaller square? If the smaller square is 1/2 the surface area. Half of them, exactly. Yeah. So you see, what we are really interested is counting when we produce n vectors, how many of them will be, with what probability they will all be inside this belt. In order to get this estimate, this is directly related to how much volume is in the belt versus the rest, right? So we use mass inside the belt and outside of belt to tell us probability that when we do random choices that our vectors end up in the belt or outside the belt.
Oh, okay, yeah.
Good.
Yeah, that answers it. Thanks.
You're very welcome. Anything else? Okay, if you don't have any other questions, I'll see you on Wednesday. See you guys.
Alex?
Yes, how are you?
Here. Can I talk to you for a sec on Teams?
Yeah, absolutely. Sure. Let us, Alex, can I ask a question about a book? Yes, please go ahead. Jojo, if you don't mind, I'll just answer.
Never mind. Yeah.
What is the, yeah, go ahead, please ask the question. I have never seen that book, you know. I don't know, but I can Google it and look through it to see. Just send me an email with the title, and I'll look through the book. No problem. Okay. Okay, Jaja, if you want, you can ask, because there are still students connected. If you want to discuss something, you can either call me on Zoom, or we can just wait until students.
But it's still recording. Maybe.
Oh, yeah, wait a second. How do I stop recording? Stop recording, stop recording. Gee. You know what? Why don't you just call me? Oh, here it is. Pause recording.